guys, so I want to go over really quickly with you all, well, semi-quickly, 10.7, which is all about polar equations. So what we talked about last time was parametric, how parametric can add that third dimension of time into a rectangular equation. Today we're going to talk about polar. This is actually one of my favorite types of equations, just because you have a lot of options for some really beautiful outcomes. So first thing we're going to talk about are plane curves. So up until this point, you have been representing a graph by a single equation involving two variables, minus parametric. In this section, we're going to study a different system. We're going to call it the polar coordinate system. So to form a polar coordinate system on a plane, we start with a fixed point O. So our fixed point O is right here in our diagram. That's kind of like the origin. And we're going to construct from O an initial ray called the polar axis. Okay, so the initial ray here is kind of like the x-axis. We're going to call it the polar axis. From there, each point P in the plane can be assigned polar coordinates. We're going to call them r comma theta. And here's the definitions for both. R is going to be the directed distance from O to P. So in essence, R kind of reminds me of vectors a little bit. R is kind of like the magnitude. R is the distance from O to P. So it's the length. Theta, on the other hand, is the directed angle. It says angle counterclockwise from the polar axis. So this is just an angle in standard form. So theta is the angle in between. All right, let's keep moving. All right, so all we're going to do is we're going to plot each given point in polar coordinates. This is so fun, so I'm excited for us to try this. This is bringing me back. All right, so first thing we're going to do, well, we need to have a length 2. R in this case is 2. So I basically could have anything from this or this or this. All of those are length 2. In essence, we're thinking like the radius is kind of 2. I want it to have an angle of pi over 3, and so I'm going to create a line that is length 2, so it's 2 long. And you can see the rungs in this case, that's actually 3, my bad, 2. The rungs represent the length here, so we can say like this is 1, 2, 3, 4, etc. in length. And I know that the angle in between that is going to be pi over 3. And so that would be the ordered pair 2, radical 3 in polar form. Go ahead and try the next ones. I think you guys can do it. So go ahead and pause and try the next ones. Okay, so I like letters B and C because in essence, they end up being the same thing. We remember from the beginning of pre-calc that negative pi over 6 and 11 pi over 6 are in essence the same thing. They end up at the same place. So we can actually, if you want, you can add, we're going to put a point where it starts. If you want, you could add an arrow to this, but the point is going to infer where this piece starts and ends, okay? But you can add an arrow if you would like. So if you want to do that, go for it. It's not really going to impact anything too much. All right, so in general, what we can say is that we have a point R. It's going to be an angle plus or minus 2n, or negative R plus or minus 2n plus 1 pi. So what this is basically saying is it's an illustration of these two. Basically what this is saying is that the ordered pair 3, negative pi over 6 and 3, 11 pi over 6, those are the exact same coordinates. In essence, they're coterminal angles. So we can say that coterminal angles, or angles that I add or subtract from negative, I cannot write and think at the same time, that I add or subtract 2 pi to, they're going to be the same. So in essence, these are coterminal angles. And thus, because they're coterminal angles, their ordered pair is going to be the same. So provided that R and R are the same, you're in essence going to get the same thing. All right, let's keep on moving. I love this. All right, multiple representations of points. So it says plot 3, 3 pi over 4 and find 3 additional polar representations between negative 2 pi and pi. So you guys go ahead and pause. I believe in you. You can do it. Okay, so the first thing I did is I graphed this, and then from there, all I'm going to do is find some coterminal angles that are between negative 2 pi and 2 pi. So first thing I could do, everything's going to start with a 3 for the most part. So everything's going to start with a 3 here. First thing I could do is I could add 2 pi to 3 pi over 4. So I could say 3 pi over 4 plus 2 pi. Well, we know that that's the same thing as 8 pi over 4. So this could be the same thing as 3 all over, you know what? I don't think that would work because that's going to be bigger than 2 pi. So let's not do that one. What we could do instead is we could find a way to get there from a negative perspective. So If I go this direction, you guys can't see this. If I go this direction here, that's going to get me 3 pi over 4 too. So that looks like 5 pi over 4. So we could say negative 5 pi over 4 is going to also be the same coordinate in polar form. So I realized I typoed on this one. We can only find 2 here. So let's go ahead and find the very last one. So the last one actually comes from the derived formula previously. So I'm going to go ahead and copy and paste that. Let's go ahead and copy and paste that like this. I also know that if I make r negative, so say instead of saying I start with 3 and I make r negative, I know that it's going to be my theta plus or minus 2n plus 1 pi. So n could really be anything. In this case, maybe we just say it's the same thing as, maybe we say n is like 0. So let's see what that would do. So say I take my theta, which is 3 pi over 4, and then we're going to say plus or minus. In this case, we'll figure out which one is going to work best for us. We're going to say plus or minus 2n, which we'll say maybe n is 0, plus 1, so 1 times pi, and we're going to see if that ends up being the same thing. Okay, so it looks like it's still going to fit on our map. So if we take 3 pi over 4 and we add pi to it, we're going to get 7 pi over 4. So this same thing as negative 3 comma negative 7 pi over 4. And I guess now that I'm looking at it, we probably could get a third one. I guess the typo doesn't matter too much. We also could do the positive. So I just did the negative. Did I do the negative? Oh, I'm just like reading this all wrong here. Sorry. Plus pi. That's positive 7 pi over 4. And then let's go ahead and subtract 2. So using the same formula, instead of doing addition here, I'm going to go ahead and do subtraction. So if we take pi away from 3 pi over 4, I think we just end up with negative pi over, I think we just end up with negative 3 pi. Yeah. So let's go and do this. So negative 3, I'm getting lost in my own translation here. Okay, so 3 pi over 4, just to confirm, minus 4 pi over 4, yes, that makes sense, is negative pi over 4. So there's actually 3 different ways that we can represent this. One is maybe a little bit more complicated using this similar formula here, but both are going to be, in essence, the same representation of the same point in polar form. Okay, let's keep on moving. Coordinate conversion. So this is the fun stuff here. To establish a relationship between polar and rectangular coordinates, let polar axis coincide with the positive x-axis. Okay, so this is kind of fun. So basically what we're going to do is we're going to put polar and x-axis on the same axis together, which is interesting. Because xy lies on a circle of radius r, it follows that r squared is equal to x squared plus y squared. This just kind of makes unit circle sense here. So if you guys were to draw like a circle, and I did not realize that was going to be filled in. If you draw a circle here, basically what we're saying is that r and y relationship, so the relationship between r, y, and x, well, they're related by a triangle, specifically a right triangle, which means I can relate them using Pythagorean theorem. R squared, which is c squared, is equal to x squared plus y squared. So this is just based on Pythagorean theorem and ideas of circles. So one thing we want to kind of keep in mind here is we're going to keep r greater than 0, using the definitions of trig functions. We usually say the hypotenuse or the distance is going to be greater than 0, which means we can use tangent, cosine, and sine to represent polar coordinates, which is awesome. So just like we did in trig class all year this year, tangent is equal to y over x, cosine is equal to x over r, and sine is equal to y over r. So the big key here is how can I convert from polar to rectangular, and how can I go from rectangular to polar? Well, say I start with polar. If I go from polar to rectangular, we can say that x is equal to r cosine of theta. So say I have an ordered pair and it's x comma y. In polar mode, it's going to be r cosine of theta comma r sine of theta. To go from rectangular to polar is going to be a little bit different. We can say that tangent of theta is equal to y over x, which relates y and x together. And we also know that r squared is equal to x squared plus y squared. So these are kind of the important things we really, really, really need to know are going to be these conversion charts. All right, let's go ahead and practice because that will be probably the most helpful for us. First thing we're going to do, we're going to convert radical 3 pi over 6 to rectangular form. So note right now this is in polar form. So I want to go ahead and switch this to rectangular form. Okay, well to do that, first thing I'm going to do is I know that x is equal to r cosine of theta. And I also know that y is equal to r sine of theta. Okay, so those are the first things that I know. Well, remember in polar form, r is my first ordered pair, theta is my second. So to go ahead and write this and solve for x and y, I'm going to get that x is equal to r, which is going to be the square root of 3, cosine of theta, which is radical 6, and y is going to be r, which is radical 3, and then sine of pi over 6. So hopefully we remember our unit circles here. All right, so cosine of pi over 6, well, that's the x value, which is going to be radical 3 over 2. So we're going to get radical 3 times radical 3 over 2, which is going to be 3 over 2. This one right here, we're going to get radical 3 times the half, so we're going to get radical 3 over 2. So to go from polar form to rectangular form, my new ordered pair is going to be 3 over 2, comma, radical 3 over 2. So hopefully that's not too bad. All right, next thing I want to do is I want to convert from negative 1, comma 1 to polar coordinates. So this is going to be a little bit newer for us. First thing they said is that tangent, we already know this, tangent is equal to y over x. We know that. We also know that r squared is equal to x squared plus y squared. So all we're going to do is we're going to plug in and solve for both. We need to solve for tangent of theta, specifically theta, and we need to solve for r. All right, let's go ahead and plug in. I know that tangent of theta is going to be equal to y over x, which is basically negative 1, right? It's negative 1 over, well, yeah, it's technically 1 over negative 1, so aka 1 over negative 1. I just plugged in. We're going to take the arc tangent. Ooh, I haven't done that in a while. All right, so we're going to take the arc tangent here of negative 1. So what this is saying is if I take two ordered pairs and I find the tangent of them, I'm going to get 1 as a result, which means I'm probably looking for something of the order of something over 4. So let's go ahead and take a look here. When does tangent give me negative 1? Well, that's going to happen in 2 different places. It can happen here, and it can happen here. Specifically, the point negative 1, 1, that's in the second quadrant, so I'm only going to look at the second quadrant, which is right here. That happens at 3 pi over 4, and so we can say that theta must be equal to 3 pi over 4, and we can say that r squared is equal to negative 1 squared plus 1 squared. So r squared is equal to 2, which means r equals radical 2. So to write this as an ordered pair, we're going to write it as r comma x. This is going to be radical 2, comma 3 pi over 4. And you'll get this with practice. All right, let's keep it moving because I have a couple more slides to do. I don't want to take all your time. All right, so to convert a rectangular equation, so this is kind of where it gets more interesting. We talked about converting points. What about equations? So to convert a rectangular equation to polar form, replace x with r cosine of theta and replace y with r sine of theta. So it's the same thing, it's just generic. Okay, so you can look at this example on your own if you want. And this is how you would solve for the following. So let's go ahead and take a look. Example, the graph of a polar equation r equals 2 consists of all the points that are 2 units from the pole. In other words, this graph is a circle centered at the origin with radius 2. So r equals 2 just means it's a graph where the radius is always 2, which is a circle. Confirm this by converting to rectangular form using the relationship that r squared is equal to x squared plus y squared. Okay, so the first thing we're going to do is we're going to start off with that r is equal to 2. That's what we're going to go ahead and start off with. So I also know that r squared must be equal to 2 squared, which is 4. Okay? So the last thing that I want to do is I want to split this into rectangular form. Well, I do know that this relationship is true. I do know that r squared is equal to x squared plus y squared, but r squared is 4. So 4 is equal to x squared plus y squared, which is the equation of a circle in rectangular form. So this is a circle with radius, if you guys remember back from algebra class, radius 2 in rectangular form. All right, so we kind of verified that one. All right, let's move on to the next question. The graph of the polar equation theta is equal to pi over 3 consists of all the points on the line that makes the angle pi over 3. That makes sense. So this whole line has an angle of pi over 3, or it has an angle of negative 4 pi over 3, which is actually the same thing as pi over 3 in terms of it being the same angle on the same line. So I want to convert to rectangular form, and I specifically want to use the relationship that tangent of theta is equal to y over x. Okay, well, let's go ahead and do that. In this case, we know what theta is. Theta is always pi over 3. So tangent of theta is equal to pi over 3, which is equal to y over x. Well, tangent of pi over 3, we're actually going to have to whip out our brains a little bit on this one. All right, so the ordered pair here, if I'm thinking about my unit circle, it's got to be 1/2 comma radical 3 over 2. So let's go and find tangent of that. Tangent is always y radical 3 over 2 divided by x, which is 1/2. Same thing as if I keep it, switch it, flip it, as radical 3 over 2 times 2 over 1, which is radical 3. And so that's equal to y over x. We could solve for x here. So if I solve for y here, if I multiply everything by x on both sides, I get radical 3x is equal to y, which actually is this linear equation that we see here. That's rectangular form. All right, let's keep it moving. Next one. Graph the polar equation r secant of theta is not evident. The graph is not evident by inspection. So convert it to rectangular form using the relationship r cosine of theta equals x. Okay, well, let's go ahead and do that. First thing that I know here, we know a couple of points. So it says this is the polar equation r secant of theta. So let's start with that. R is equal to secant of theta. Okay, well then what we can do next is we can replace r in the next equation. So r cosine of theta is equal to x, cosine of theta, except I know r is secant of theta. So I'm going to replace r with secant of theta. So now this is secant of theta times cosine of theta, I don't know why I wrote 0 there, is equal to x. But secant times cosine is the same thing as 1 over cosine of theta. What a nice throwback, times cosine of theta, which, I keep writing the wrong things, which cancels to 1. So this must be the line, which is vertical. 1 is equal to x. Okay, so those are some just basic problems here, but kind of the big goal for today is I want to put together polar form and rectangular form and parametric form into one project. In fact, I want to create something, I hope, beautiful. So what I want to show you is just some interesting cases in polar form. So I think that I can show you my calculator right now. I'm hoping. If not, I'll cut this out. So I wanted to show you guys just some interesting cases. So let's just talk about some interesting, just like we did last time. Let's talk about some interesting polar cases. So in your calculator, to get polar mode, all you're going to do is press onto mode and go down to the fourth one down, and I want you to scroll over to polar and press enter. On there, it's going to say R1 is equal to something. So we're just going to kind of guess around and see what we're getting. Let's try this. Let's say that R1 is equal to, I don't know, R, we'll say, maybe we call it cosine of theta. Let's see what that looks like. Okay, so if I graph cosine of theta, I get kind of like an oval looking shape. Let's see what happens when I graph sine of theta. So instead, let's graph sine of theta. Okay, so I get kind of the same shape, but it's moved. Let's say that I say 2 sine of theta instead. 2 sine of theta. Let's see what that one looks like. Okay, so I get a bigger oval. Kind of makes sense, right? If I make sine multiply by something, it should get bigger. What happens if I make sine bigger on the inside? So let's say I do sine of 2 theta. Ooh, that is very interesting. That is super interesting. We got ourselves a flower. So my question is, why do you think that we would get this shape here? Well, the trace function is going to really tell us why. So we're going to press the trace function. And I'm just going to trace through. So what this is saying is that x, which is r, is going to be our polar coordinate, and theta is going to be how many degrees I'm doing. I want you guys to see how this traces. Notice how it follows maybe not the most intuitive pattern here. So I want to know specifically, why is this happening? So as I scroll around, this is what's happening. Let's go back to the beginning and see why this is working the way that it is. Okay. I guess I could just start it over. Okay, so I know that this is the equation r equals sine of 2 theta. So we'll say r is equal to sine of 2 theta. When r, the length, is 0, we say that theta is going to be 0, okay? But as r gets bigger, say r gets a little bit bigger. In fact, maybe let's make r equal to pi over 2. So let's try this one. Say r gets bigger. It's pi over 2, which is like 1.5-ish, okay? Let's go and scroll and see what happens. When r is pi over 2, or about 1.5, let's see what happens. Happens a little later than I think. Oh, I'm not pressing the real trace button. There we go. Sorry. Trace. There we go. Let's look for r, which is x. We want to know when is r about 1.2. Keep on going. But you know what? This might not be the best way to look at this, because I guess theta. We'll go back. All right, so when r is equal to 1.5, I'm just going to plug in and show you what this looks like. So when r equals 1.5, we're going to get sine of pi over 2 times 2, which is just going to be sine of pi. And sine of pi is equal to 0, which is why I picked a bad one. It's not going to show up on the graph. So basically, when we're saying when r has length 1.5, theta, in essence, is 0. So this thing is actually probably not going to show up necessarily on our graph. Let's pick something maybe a little bit easier. Let's go ahead and pick like pi over 4. That actually, I think, should show up. So let's try this one. Let's say r is equal to pi over 4. If r is equal to pi over 4, then I have sine of pi over 4 times 2, which is going to be sine of pi over 2, which should be 1. So let's go ahead and take a look at this. So I'm going to look for when my theta is about 1, which should be up here. Let's go up a little bit. Okay. So when theta is about, too far. I'm always going the wrong way here. Here we go. So when theta is about 1, we can see that r, the x, is like 0.58, which is about pi over 4 here. So what this is doing, it graphs in a really different manner. It's not necessarily in a linear fashion. It kind of loops around. But basically, we're saying that every time I change r, I change the theta. And if r is the distance and theta is the angle, the relationship between r and theta doesn't necessarily have to create a function. So it is an interesting property that's going on here, and we'll probably talk about it more when I'm actually in person. But I do want you guys to kind of mess around on your calculator, see what kind of images you can make using sine and cosine, and then see what images you can make just in general. All right, so I know this video has already gone too long, so that is it for today. I am going to post information about your project. Just be thinking to yourself, what kind of shape could I make using polar, parametric, and maybe just a touch of rectangular. All right, I hope you guys have an awesome day.